Okay, we are looking at our fourth chemical reaction, which is called double displacement or double replacement reactions. When we have a double displacement reactions, you are going to have two compounds coming together, and essentially they're swapping partners, and you're going to form two new compounds. So when we take a look at this animated GIF, we have silver nitrate reacting with potassium chloride to form silver chloride and potassium nitrate. So what we have happening in this scenario is the magnesium, which is the metal, gets swapped out, and it's also referred to the cation. So the cation is always the first part of a compound name, and the cation will become the cation of the new compound, and the anion will become the anion of the new compound. So essentially, like I said, if we have this scenario where you have couple AB, couple CD, what happens is the A swap places with the C, so the positive ions swap places, and essentially you end up with two new compounds. So we're going to take a look at how that happens. So we have two types of double displacement reactions that can occur. We have what we call precipitation reactions. And I want to refresh your memory on what a precipitate is. Recall that a precipitate is when you have two aqueous solutions coming together and you form a product that is slightly more gelatinous or thicker, more viscous than it was before. And the precipitate will often have some sort of color. So in this particular case, we are having the precipitate called lead 2 iodide being formed, and it is a yellow, thicker substance. So that's what a precipitate is. Okay, now let's take a look at this reaction here. You have magnesium sulfate reacting with sodium fluoride. In order for double displacement reactions to occur, they have to be in solution. They have to be aqueous. Now, how do we determine whether something is aqueous or whether or not is fairly insoluble, meaning it doesn't like to dissolve? What we do is we can use this solubility chart. There's this version or there's this version. So when we take a look at this version over here, we find magnesium, we find sulfate, and we look at where they intersect. And we see that it says AQ. Okay, so AQ means aqueous. It's dissolved in solution. When we use this chart, we find where it says sulfate, and it says everything that hooks up with sulfate is soluble except calcium, barium, strontium, mercury 2, lead 2, and silver ion. So this is considered to be aqueous. So we would write an AQ in the brackets to show the state. Okay. Now sodium fluoride is the same. If I go find fluoride above here and I look for sodium, I see that it is also aqueous. So we put an AQ. Sodium sulfate, let's take a look. Well, let's use this chart. Is this soluble when a new product is made? Will it stay dissolved in solution, or will it cause a precipitate to form? So what we do is we take a look. Here's sulfate. Everything is soluble except for these ions. So this falls in the category of being soluble. So we'll write down AQ. When we look at magnesium fluoride, I see that fluoride isn't one of my options here for ions, so I have to use this table here. So magnesium fluoride, let's look at fluoride, and I go find magnesium. Okay, so there it is. And I notice that an S means that it is a solid. Okay, so S means solid. So this happens to be our precipitate. Okay, let's take a look at what happens in solution at the molecular level. So here, in order for double displacement reactions to occur, you have to have the two reactants that are aqueous. So when we put them in solution, the ions become mobile. Okay, and then what happens is over time in solution, they will collide. And if you get the magnesium and the fluorine colliding, then you will get something that is a solid precipitate. Okay, so let's take a look here. The magnesium ions and the fluorine, perfect. So that solid gelatinous material will start to form and it'll settle towards the bottom of the container. The sodium sulfate, however, remains aqueous. So that means it stays dissolved in solution. Now, when we are writing precipitate reactions, these double displacement reactions, I'm going to show you how to write what's known as a molecular equation, which you already know how to do. That just is a fancy word for saying a balanced chemical equation. So here we would have to put a 2 in front in order to balance the sodiums and the fluorines. You have to indicate the states. So that is our basic molecular equation. Then there's something called the ionic equation. This is where you take each of your aqueous substances and you break them into their respective ions. So you have to show the charge. So we know the charge on magnesium is +2, sulfate is -2, sodium is +1, fluorine is -1. Those are all aqueous. So as we saw in the beakers, those are mobile ions. These also remain mobile in solution. Okay. The only thing that's precipitating out, forming a solid, we keep that intact. Okay. So in an ionic equation, those guys are no longer free floating ions. They come together to form that solid. Now, the other thing that we have to be mindful in an ionic equation is that we have to balance those ions. So this coefficient of 2 applies to both the sodium and the fluorine ion. Okay. So the fluoride ion. So you have to balance those. And this little 2 here applies to just the sodium. So hence why a 2 goes in front here, and this 2 applies to both of those ions. Okay. Now what we're going to notice is there are common ions to both sides of the equation. The sulfate ion is common to the left and to the right, and we also have another common ion, the sodium ion. Okay. Whatever is common to both sides of the equation, we actually cross those off. Those are called spectator ions. Okay. So when we cross those off, we're left with just the ions that are needed in order to make the precipitate. So those are called molecular, ionic, and net ionic, and I'll show you how that works in a separate lesson. Okay, so again, the ions that are not involved in the making of the precipitate, the ones that get crossed off are called spectator ions. And when we write that final net ionic equation, the reason why we do that is just to show the ions involved in the making of the precipitate and to also simplify that reaction. Now, the second type of double displacement reaction that we are going to encounter is called a neutralization reaction. You will have seen this before, perhaps in grade 10, where you take an acid plus a base yielding a salt in water. This really is just a fancy type of double displacement reaction. Okay, so you need to remember acids plus bases always yield salt and water. Now, the hardest part when it comes to acid-base reactions is identifying if you actually have an acid and a base as a reactant. And what you have to do is you know that anything that ends with the word hydroxide is going to be a base. So those are the more common ones that we're going to do. The acids, here's a list of all the common acids that we should be familiar with. Whenever you take a halogen, so anything from the halogen family, the 7th family on the periodic table, and you hook it up with hydrogen, so just HCl, HBr, HI, and we have AQ written beside it, it becomes an acid, and we call it hydrochloric. We always end in ic, hydrobromic, or hydroiodic. If this was HF, it would be hydrofluoric. So that is how we name those type of acids. Those are called binary acids, meaning made up of 2 elements. When we get into these polyatomic acids, or sometimes we refer to them as oxyacids, they have oxygen in their structure, okay? And we notice that if I took a look at all of my 8 ions, nitrate, sulfate, carbonate, if it ends in 8, okay, and I look at the charge, so if I look at nitrate and I add however many, whatever my charge is, and I add that many hydrogens onto the front, then I can make an acid. So because the charge on nitrate is -1, if I add 1 hydrogen onto there, it becomes a neutral compound, and we call it nitric acid. When I look at the charge on sulfate, if it's a -2, I put 2 hydrogens onto the front, H2SO4, and it becomes sulfuric acid. Notice it ends in ic. If I take a look at carbonate, I look at the charge on carbonate, it's -2. I add that many hydrogens onto the front, H2CO3, that becomes carbonic acid. If you look at all of your ite ions, so nitrite, sulfite. Notice that ite ions have one less oxygen than the ate ion. So if we look at these two here, nitrite, okay, we put that many hydrogens back onto the front, and instead of calling it an ic acid, it is an us acid. So ite ions always make us acids. So this is nitrous acid. If I look at sulfite, okay, one less oxygen than sulfate, the charge still remains the same. So I put that many hydrogens onto the front, and you make sulfurous acid. So ite ions always make us acids. Ate ions always make ic acids. Okay, so you can always refer to this chart to help you, but you needed to kind of know where that came from. Let's take a look at an example with an acid-base reaction using hydrochloric acid and sodium hydroxide. Just as we saw with the precipitate reactions, you have to have both of these reactants in aqueous form. So when we dissolve hydrochloric acid in water, the ions become mobile. Only then can they swap partners. So as you can see, the sodium and the hydrogen are going to swap partners, and you get sodium chloride, and you also get water. So then what we're going to do is we're going to take a look at this reaction here, where we've actually taken some of the hydrochloric acid and the sodium hydroxide, and I'm going to add them together. Okay, so let's pour some of those together. Okay, now nothing seems to be apparent in what is happening at the moment. Okay, so what I'm going to do then is I'm going to take some of that, and I'm going to put it onto an evaporating dish, and then I'm going to heat up that solution there. And over time, what I'm going to do is I'm going to evaporate the liquid, and I notice that I am left with this white powdery substance, and that is your table salt. This is what essentially happened. Aqueous sodium hydroxide, aqueous hydrochloric acid. When we swap the partners, we see that we get sodium chloride, which is aqueous. We didn't see any of that initially, okay? And we also had water. When we evaporate the water, we are left with that solid sodium chloride, okay? So we had evidence. And if we had tasted that, it would have tasted like salt, okay? If I was to write the ionic equation for this, we cross off what's common to both sides, and we would be left with the two ions that make up liquid water. Okay, so remember, anything that's aqueous gets broken up into the respective ions. Anything that is a liquid or a solid, we leave as is. Okay, so here's another example of a neutralization double displacement reaction. You have sulfuric acid. Okay, we have to watch out for those. We have barium hydroxide. When we swap the partners, okay, we've got the cation swapping places with this cation. We end up with water. Okay, so there's the H and the OH hooking up to form H2O, and we get the barium hooking up with the sulfate, so we get barium sulfate. So the states for this reaction would be liquid water, and this would be aqueous barium sulfate. Until we evaporated the water, we could then get back that salt. Okay, there you have it. Double displacement reactions, a little bit of an intro there for you. Let's move on to the actual lesson.